Hello everyone. Today I will explain a problem where we calculate the sum of remainder. Step 1. We started with two numbers. N is starting number, M is divisor. Step 2. Make a list of number for n. For example, n is 10. The list is 10, 9, 8 into 1. Step 3. Take each number divided by m and find the remainder. For example, if m is 4. 10 mod 4 is equal to 9 mod 4 equal 1, 8 mod 4 equal 0. Keep doing unit to reach 1. Step 4. Add all reminders. For example, reminders are 2, 1, 0, 3, 2, 1 into 0. And their sum is 9. The final answer is 9. Thank you.
Hi everyone. Today we are diving into a problem called the pairwise sum and divide problem. Given an array, let's call it A with n element. The goal is computed cumulative total T by applying specific formula to pair of element in the array where the should index greater than the first. For each pair of element, we calculate value for I and j using the formula AI plus AJ divided by AI by AJ. Finally, we sum up these results for all pair to get T. Let's work through an example. Take array A equal 1, 2, 3. First, we list all pair where the second index is greater than the first. First, 1, 2, 1, 3, and 2, 3. Now apply formula for each pair. For pair 1, 2, the result is 1. For 1, 3, it is 1. 2, 3, it is 0. Finally, sum of them. The total T is 2. That's our result.
Let's look at the problem about power and find the last two digits of a sum. The sum S is made by adding numbers raised to a power, like this. S equals 1 to the power n plus 2 to the power n plus 3 to the power n up to k to the power n. To get last two digits, we calculate S mod 100. For example, shall we take k as 4 and n as 4? We can calculate 1 to the power 4 equals 1. So 1 to the power 4 mod 100 equals 1. 2 to the power 4 equals 16. So 2 to the power 4 mod 100 equals 16. 3 to the power 4 equals 81. So 3 to the power 4 mod 100 equals 81. 4 to the power 4 equals 256. So 4 to the power 4 mod 100 equals 56. Now we adding these, we can get S equals 154. Finally, S mod 100 equals 54. So last two digits of S are 54. This shows how modular arithmetic make working with large numbers easier.
Scalar product. This problem involves generating a sequence and calculating the scalar product. First step is identify parameters. Start with A0 equal to 0 and A1 equal to C. So use the M as the modular and N as the number of vectors to define the limits. Second step is generate the sequence. Apply the formula AX plus 1 equal to open brackets AX plus AX minus 1 close the bracket multiply by M. Third step is pair coordinates. Use the sequence to form vector pairs as V1, V2 to Vn. Also, we can represent them as the X1, Y1, X2, Y2 and Xn, Yn. As you can see, this one is the example of scalar product.
Summing the Kn series. This problem involves calculating the sum of selected terms in numerical patterns using formulas. Two main types of series are addressed. First one is arithmetic series and then geometric series. In arithmetic series, the formula is Sn equal n over 2, open brackets, 2a plus, open brackets, n minus 1, close brackets, terms d. The key steps of this arithmetic series are identify the common difference between terms, then determine the first term and the number of terms, and lastly, use the formula to compute the sum. When we talk about the geometric series, the formula is Sn equal a terms, open brackets, 1 minus r to the power n over 1 minus r. The key steps are identify the first term, the common ratio, and the number of terms, and then substitute into formula to find the sum. Lastly, as you can see, there are two example problems of arithmetic series and geometric series.
This problem involves analyzing a series and answering two types of queries. First one is count-based queries. We can count how many numbers in a specific range satisfy a condition. For an example, in the series 13579, if asked how many numbers between the second and fourth terms are divisible by 3, we can check each term in the range. Here, only 3 satisfy the condition. And the second one is calculation-based queries. We can perform calculations on specific terms like summing 2 terms and finding the result modulo a given number. For example, summing the second and fourth terms and taking modulo 5 gives us 0. In brief, the process is to identify the starting number, difference, and length of the series, extract the required terms based on the query, apply the conditions or calculations to get the results. As the example outputs, count numbers greater than 4 between second and fourth terms is 2, and sum of the second and fourth terms modulo 5 is 0. In short, we can analyze the series, process the query step by step, and calculate the results accordingly.
Everyone, today I will be presenting the circle summation problem, a mathematics simulation involving children's numbers and a circular process of modifications. Let's dive into the details. The circle summation problem involves capital N children arranged in the circle. Each children start with an initial numbers. The game consists of capital K rounds, where in each rounds and one child modifies their numbers by adding the sum of their two neighbors' numbers. The goal is to find the resulting numbers for all children after capital K rounds, starting with every possible child in the circle. A key elements of solving this problem in the transistor matrix. This matrix represents the influence of neighbors. Each row corresponds to a child and the columns represent the weights of the contributions from other children. For example, for 5 children, 10 matrix ensure proper summations of neighbors in a circle manner.
Let's now talk about the counting equation question. First, we represent the system as a metric equation Ax equalized to B mod P. Here A is a matrix of coefficient, X is the variable vector, and B is the result vector. To find the number of solution, we use the formula number of solution equals P to the power n minus rank A. Next, calculate the rank using D equals n minus log base P S. Here S is the number of solutions. Adjust the rank if 0 entries or fixed variables are involved. Now, to count valid configuration, the total ways are P to the power m minus d into n minus z, where z represents fixed variables. For an example, let's take the equation ax plus by equals n, where a, b, x, y are integers. Start with x equals 0, calculate y using y equals n minus az over b, and ensure it's a whole number because it cannot be an integer. Iterate x from 0 to n over a. And check divisibility for n equals 5, a equals 2, b equals 3. A valid solution are x equals 1 and y equals 1.
Hi everyone, today we are diving into an interesting problem called XOR love. The problem starts with two inputs, n the size of an array and q the number of queries. For example, if n equals 3, we create an array A as 3 to 1, counting down from n to 1. For each query, you will also receive 3 integers k, p and r. Now, for each query, the goal is to compute a cumulative result called KPR sum. Here's the workflow. Step 1. Start with sum equals 0, and if p equals r, we immediately return 0 for this query. Why? Because valid pairs I and j requires j greater than I, and that's not possible if p equals r. Otherwise, we process the array elements within the range p and r. Inside the range p and r, we loop through each element I and pair it with every j such that j greater than I. For each pair, calculate XOR of ai and aj. Then XOR this result with k. Add all these values to the sum. Finally, take the modulus of the sum with 10 to the power 9 plus 7 to ensure that result doesn't overflow. Once all queries are processed, print the result of KPR sum 10 to the power 9 plus 7 for each query. And that's it.
We'll explore rational sums and their convergence. What is a rational number? Rational number is any number that can be written in the form of P over Q. P and Q are integers where Q is not equal to 0. We'll be taking a series term where I'll be taking 1 over n into 1 n plus 1. We'll decompose this into partial fraction, and the term will be getting a equals 1 and b equals minus 1. We'll be giving n equal 1, n equal 2, n equal 3, and we'll be finding the last term where I'll be getting 1 over n minus 1 over n plus 1. After the terms get cancelled, we'll be getting 1 minus 1 over n plus 1. The last step will be to evaluate the limits. Limits n goes to infinity, 1 over infinity is equal to 0. Therefore, the term 1 over n plus 1 goes to 0. The series sigma n equal 1 infinity 1 over n into n plus 1 will become 0. It will become 1. This makes a convergent series.